All right. Good evening and welcome to Turbo Intruder, abusing HTTP misfeatures to accelerate attacks. Last time that you made a serious effort to hack into a website, I wonder how many HTTP requests you sent to it. Maybe 10,000, possibly 50,000, maybe up to 200,000? Guessing the names of things like files and folders and usernames and passwords and so on is a core part of any web application audit, because finding that one folder that the developer completely forgot existed can be the difference in between taking complete control over a website and getting absolutely nowhere. I vividly remember the first time that I ever tried this technique. I ran this tool, which is called OWASP Dirbuster, and it was like, hey, I found this folder called sales. Maybe you should check it out. So I loaded up /sales in my web browser, and my web browser nearly crashed because the website had decided to just give me the personal details of millions of users with no password or authentication or anything. And ever since that, I've been a great fan of this technique. But every time that I cancel a brute force attack, I find myself wondering, if I had left that running for maybe 10 more minutes, or just sent an extra few thousand requests, perhaps I would have found something really interesting. Or maybe, if I'd sent my requests 20% faster, then the server would have just flipped out and started dumping access logs into the responses that it sent to me. And I'll never know, but in this session, I'm going to introduce a tool designed to solve all of our brute force problems by using a custom HTTP stack to send requests as fast as possible. So first, I'm going to talk about what makes Turbo Intruder fast and how you can use the same techniques to make your own tooling fast. After that, I'll show you how to use it and then look towards the future of what can be done with that, and then hopefully take a few minutes of questions. So our objective is to send HTTP requests as fast as possible. Hopefully most of the people here are familiar with what a HTTP request is, but if you're not, from this point of view, it's just a question that you ask of the website, like, is there a folder called sales? Or does the user admin have the password, let me in? That will normally require one request. Now, tools that have done these kinds of attacks in the past have traditionally focused on achieving speed, on achieving loads of requests in a short amount of time by making a lot of concurrent TCP connections and sending one request per connection, like you can see here. And like you can see here, because of that approach, they're wasting a lot of time doing this TLS handshake that's a waste of time. So what I want to show is that this approach is terrible and there's a much better way of doing it, and that's to kind of drill down and focus on getting the maximum possible speed with one concurrent connection. And then we can increase that as necessary afterwards. Now, has anyone ever heard of a security scanner called Skipfish? No. Oh well. This scanner is pretty old. I don't blame you for not having heard of it. I don't think it's been maintained in about 10 years. But the key thing about the scanner is that it is really, really fast. It was actually the inspiration for me to make Turbo Intruder. And I initially thought the reason that this tool was so fast was because it was coded in C with speed in mind. And that kind of is, but the core reason is because it reuses TCP connections as much as possible. So it will send maybe up to 100 requests over one connection, which results in it going with a single thread around 400% faster, which is pretty nice, right? So the original version of Turbo Intruder was simply a hacked up version of Skipfish. But then I found something that could be used to make it even faster. There's a technology that's not very well known called HTTP pipelining. Now, this is supported by almost all web servers, as far as I can tell, but no modern web browsers use it because it's too unreliable. But for our purposes as a hacker, it's just fine. And how this works is you send all your requests back to back before you bother reading in anything from the server. So you're relying on the server sending the responses back in the order that you sent the requests in, which does backfire sometimes, which is why web browsers never use it, and more or less why HTTP 2 was made, I think. And so what that means is the effects of the server processing time and the latency on your request throughput are completely minimized. And I found that using this with a single thread on a particular target, I was able to go at 6,000% of the original speed, which was pretty cool. And that was so fast that when I then took this and made it start using an asynchronous networking stack, thinking that that would make it even faster, it made no difference because the number of concurrent connections that I'm using here isn't the bottleneck anymore. And that is a great situation to be in because a whole bunch of firewalls and servers rate limit requests by limiting the number of concurrent connections. And what this is saying is I'm only going to use a tiny number of concurrent connections. So your firewall is going to let me through, but I'm still going to be able to send requests really, really fast. You might be wondering where HTTP 2 is on that diagram, and the answer is I tried it and found it goes at pretty much exactly the same speed as HTTP pipelining, but it's less widely supported, so I haven't maintained that. So that's all the theory, pretty much. Let's have a look at how you actually use it. So Turbo Intruder it's an extension for Burp Suite. It works in the free version, and once you've installed it, you just highlight where you want to inject, and you right-click and send to Turbo Intruder, which pops open a window, which looks like this. And in the top, we have the request that we just sent here, and the rest of it is a snippet of Python. And you might be thinking, hang on a second, if I'm going to write custom Python code, then I might as well just write it the normal way and use some other library. But if you use some other HTTP request library, that probably won't support pipelining, so it will go way slower. And also these libraries don't generally support malformed requests, which as hackers we're quite likely to want to send. So the underlying implementation is here. You're using a request engine, which is a library written in Java, but you're talking to it through Python, which just makes it easier to modify. So let's take a closer look at the code. To begin, we just have a simple snippet to set up the request engine, and you could leave that as is and just not touch it, and your attack will probably go pretty fast. But if you want to get the maximum speed possible for your attack, then you might want to tune those values there. After that, all you need to do is open your word list or whatever you're going to generate your requests with and queue up the requests. And then the final thing is there's a separate function which gets invoked every time you get a response. And in there, you need to choose, you need to work out whether that response is interesting, and therefore whether you want to stick it in the results table. If you put everything in the results table, you will run out of RAM quite quickly because you're probably running so fast. Yeah, so that's the basic attack, and that's the kind of the default template. And to be honest, to change that in a basic way, you don't really need to know any Python. It's pretty easy. And this is a streaming attack, which has certain advantages. So here's a screenshot of an attack that I ran overnight at home on a residential connection that's not particularly fast, just on a normal desktop, and just sending traffic to my own server which is hosted in London. And if we look at the bar at the bottom, this has been running for 17 hours. We've sent an average of 22,546 HTTPS requests per second, resulting in a total of 1.4 billion requests. And if we look at the memory usage, we haven't used up more than 3 gigs at any point, and that's the memory usage for the whole of Burp. So most of that is being used up by Burp and not Turbo Intruder. And by doing that, we've successfully brute forced this 7-character string, which is completely random, which you might have thought would be a secure password, for example. But with this, we can just crack that really easily on the web. Okay, let's take a closer look at this tuning process with a live demo running over the Wi-Fi here. Hopefully the account I'm using is not going to get anyone in any trouble. Last time I did this, it was in a pub and the Wi-Fi was so bad I had to steal it from next door, which was Starbucks. So here I've got this basic request, just fetching this robots.txt, and the first thing I'm going to do is just make this request as small as possible in order to reduce the amount of stuff that I have to transmit over the network. So if I send that, still works. Great. Now I'm going to select where I want to inject and right-click, which is really quite challenging on this trackpad. I should have added a keyboard shortcut or something for this. Right, there we go. And then send to Turbo Intruder. And we can see the request is up there. This placeholder has appeared where I selected. And this is a fairly basic attack. So I'm just going to use this word list, which is present on all Macs. And at the moment, I'm going to set this running with 1 request per connection. Right, so this is the old school way of doing it. And if nothing goes wrong, yeah, something's gone wrong, it's jammed. This is definitely the Wi-Fi's fault. Okay, right, so here, it's running now. We can see we're doing about 18 requests per second there. And there you can just see what the next word in the word list is. So 18 requests per second is the base speed here, right? So now I'm going to start reusing connections like Skipfish. So that means I'm going to send 100 requests per connection, and you can immediately see I've jumped to 80 requests per second. So we're going about 4 times as fast. So that's nice. And now I'm going to turn pipelining on, which is what makes Turbo Intruder particularly fast. And if nothing goes wrong, this is going to go quite a lot faster. Right, yeah, you see we've jumped to about 1,000 requests per second, which is not bad for Wi-Fi. We've even found something. And now I can try and increase the number of concurrent connections. And I haven't explored what value I should set this to for the Wi-Fi, so I'm just going to set it to 4 and see if it goes a bit faster. Right, there you go. So now we're on about 4,500 per second. In my office, I can reach 10,000 per second over Wi-Fi and 30,000 over Ethernet. Yeah. So that's pretty cool. Oh yeah, well, one more thing. All right, what if I set this to 200? So it's going to send 200 requests per connection now. Will it go twice as fast? It's going to go about the same speed, but this retries count has started shooting up, which is this saying that the server is dropping the connection a lot of times. And that's because that server only allows 100 requests per connection. So if I go back to that, then the retries should more or less stay on 0, which tells us everything is more or less fine. Okay, so that is how you use it. Now, that was a streaming attack, which is great for memory usage, but if you want to find a race condition, then that's the opposite of what you want, because with a race condition, you want all your requests to hit the server at exactly the same time. So this is a setup to find a race condition. The only thing that's changed is that the request.start line has moved to after the engine.queue line. So that's saying queue up all the requests, and then when they're all ready, send them on. Why might we want to do that? Well, you can do some quite cool things with race conditions. So here I'm trying to buy a Tiffany highball glass from a website hopefully no one recognises. And the cart total is $65, and I've got a discount code that gives me like 20% off. But I'm going to use a race. I'm going to try and use a race to apply it multiple times. And by using Turbo Intruder, if you look closely, you can see I've achieved a discount of $84, resulting in a total price listed of negative $19, which is a pretty nice bargain. So that's the gist of Turbo Intruder. Now, I'm just going to talk about what we can do with it next. So these are all the manual steps, and it's a bit of a headache to do all of these every time, especially if you're trying to do it loads and you're really lazy. And I think all of these can be automated, but the one that's the most tedious is the response screening, as in is writing that callback function, which works out what's interesting and what isn't interesting. So I've automated that. So I used some fancy logic that I talk about in great depth in my presentation on /pad scanning. But basically, if you open Turbo Intruder, you'll see these extra lines which have been highlighted with that learn parameter. And that learn parameter tells the engine the response that you get from this request is boring. I'm not interested in that. And so the request engine then sets the value of the interesting value in the callback lower down, based on whether the response matches the boring one or not. And because of the fuzzy diffing logic and so on, it's pretty good at doing that. And the end result is that generally you don't need to change any of that code, and only interesting findings will appear in your table. Of course, you can play with that if you want to. So maybe you're trying to brute force folder names on a server which has a web application firewall which is dropping every request with the word admin. So then you can say, actually, requests with the word admin, say the response to the word admin is not interesting, and that way your table won't get flooded with boring findings caused by the WAF. So yeah, with that, with no action of ourselves, we get handling of basically any kind of enumeration, stuff like username, host header, cookie header, file folder, whatever, and it's quite fine-grained, which means it can find some quite small changes. For example, on one site, if you try and log into someone's account loads because you're trying to guess the password, you get this message back. Your IP has been locked out because you've tried to log in too much, right? Fair enough. But Turbo Intruder doesn't care. It will keep running. And if it happens to try the correct password, it will get this response back. And that response is slightly different because it doesn't say invalid password. So it will then go, well, that's interesting, and it will put that in your table, and you'll go, oh, that's the password. All I need to do now is wait for 5 minutes. I'm unbanned. I can log in. Great. So effectively, their brute force protection is completely useless. So what next for Turbo Intruder? Well, I was going to say I'm going to make it work headlessly on servers in case you're stuck using bad Starbucks Wi-Fi, but I did that yesterday, so it does that now, just about. It would be interesting to cluster results. So if you've got a bunch of results in a table that are the same, it will be nice to automatically group those. It will be nice to recognize when the server is overloading and experiencing problems and then automatically slow down. Yeah, because otherwise that can happen. But the thing I'm most excited for is semantic word list generation. So this is where I go, well, Turbo Intruder knows what the original input was, right? You know, maybe it was an 8-digit number. And that means, well, since the server is expecting a number, maybe Turbo Intruder could try other numbers that it's seen in the traffic on that website. And if that's an organization ID, thanks to that technique, it will try other organization IDs, which might have more interesting reactions from the server than simply sending random things in. And with some things like numbers, that's really easy. And with some things like host names and usernames, it gets progressively harder. But I think you could write a generic solution that will do a reasonably good approach most of the time. Okay, so the three key things to take away from this presentation are that the technique you use is more important than the number of concurrent connections. Total automation of these kinds of attacks, where as a user you barely have to do anything, is just about within reach, and we definitely need some bigger word lists. Now, you can grab this tool from that URL. Also, I'm going to put it on GitHub when this recording is uploaded. I'm going to answer 5 minutes of questions now, and if you have any more after that, just come and speak to me at the back or chuck me an email. Don't forget to follow me on Twitter. Thank you for listening. Sure. Any questions?
How does it relate to Heartbleed? Is it similar to that sort of thing? Is it like an SSL?
No, not really. It's a HTTP thing. It isn't an attack in and of itself. I'm just taking advantage of a feature that no legitimate people use. Yeah. Cool. Thank you.